In microwave engineering, a transmission line is only perfectly matched and predictable when it is completely uniform. The moment you change its geometry, by stopping it, bending it, splitting it, or changing its width, you disrupt the smooth, continuous flow of the electric and magnetic fields. We call these disruptions discontinuities. When the fields are disturbed, they have to reconfigure themselves. This reconfiguration stores localized reactive energy. If the discontinuity causes electric field lines to concentrate or fringe out into the air, it stores electric energy and acts like a parasitic capacitor. If the discontinuity forces the physical current to squeeze together, crowd a corner, or take a detour, it stores magnetic energy and acts like a parasitic inductor. Open-ended microstrip. The physical structure. The microstrip copper trace simply stops abruptly. Field behavior. You might think that because the copper ends, the electric field stops cleanly. In reality, the electric field lines fringe or bleed out from the open edge, extending slightly into the air and the dielectric substrate just beyond the physical cutoff point before returning to the ground plane. Equivalent circuit and impact. Because these fringing fields store extra electric energy, the open end is modeled as a small shunt capacitor, see end, connected to ground. Practically, this means the microstrip electrically behaves as if it is slightly longer than its physical length. We call this the length extension, delta L. If you are designing a precise half-wave resonator, you must physically cut the copper trace slightly shorter than half wavelength to compensate for this fringing capacitance. 2. Short-ended microstrip, plated via hole. The physical structure. The microstrip trace is connected to the bottom ground plane by drilling a hole through the PCB and plating the inside of the cylinder with copper, a via. Field behavior. The current traveling along the wide, flat trace must suddenly converge and funnel itself down the narrow, cylindrical wall of the via. Equivalent circuit and impact. Because the current is heavily crowded and must travel a vertical distance, the thickness of the substrate, it generates a localized magnetic field. This means a via is never a perfect 0-ohm short circuit at microwave frequencies. It is modeled as a series inductor, L via, to ground. At incredibly high frequencies, millimeter wave, this parasitic inductance can become so high that the via acts like an open circuit or even begins to radiate energy like a tiny antenna. 3. Gap in microstrip. The physical structure. A single trace is cut in half, leaving a small physical air gap between two open ends. Field behavior. This combines two open ends facing each other. Electric field lines fringe from the left open end down to the ground, from the right open end down to the ground, and they couple directly across the air gap from one trace to the other. Equivalent circuit and impact. This is modeled as a capacitive pi network. There is a series coupling capacitor, Cg, bridging the gap, and two shunt capacitors, Cp, to ground for the fringing fields of each edge. Gaps are used intentionally to build DC blocks, allowing high-frequency AC microwaves to jump the gap while blocking DC voltage, or to loosely couple energy into a resonator filter. 4. Change in width, step discontinuity. The physical structure. A sudden, abrupt jump from a wide trace, low impedance, to a narrow trace, high impedance, or vice versa. Field behavior. As the wave moves from the wide section to the narrow section, the wide, evenly distributed current must abruptly squeeze together to fit into the new trace. Conversely, going from narrow to wide, the current violently fans out. Equivalent circuit and impact. This current crowding creates a concentration of magnetic energy, modeled primarily as a series inductor, LS. There is also a small shunt capacitance, Cp, because the exposed corners of the wider trace allow electric fields to fringe down to the ground. If not accounted for, a step discontinuity will cause a reactive phase shift that can detune an impedance matching network. 5. Tapered microstrip line. The physical structure. A gradual, smooth transition from a wide trace to a narrow trace, rather than an abrupt step. Field behavior. By slowly changing the width over a distance of at least 1/4 wavelength, the current is allowed to gently funnel together, and the electric fields smoothly adapt to the changing geometry. Equivalent circuit and impact. A taper effectively eliminates the lumped parasitic inductance and capacitance of an abrupt step. It acts as a broadband impedance transformer. The trade-off is size. An abrupt step takes up 0 length, whereas a taper, like a Klopfenstein or exponential taper, requires significant physical board space to execute the smooth transition. T-junction. The physical structure. One trace splits orthogonally into two traces, forming a T shape. Field behavior. This is a violent disruption. Current traveling up the stem of the T must slam into the top wall, split, and make a sharp 90-degree turn in two different directions. Simultaneously, the electric fields pile up at the sharp inner corners of the junction. Equivalent circuit and impact. The T-junction is incredibly highly reactive. It is modeled with a large shunt capacitor from the electric field pooling at the corners and a star network of 3 series inductors from the current crowding as it splits. T-junctions cause massive reflections. To fix this, engineers often cut V-shaped notches into the junction to remove excess capacitance and guide the current more smoothly. 7. Bent microstrip line, right angle bend. The physical structure. A standard 90-degree turn in a trace to route a signal around a PCB. Field behavior. When a wave hits a 90-degree corner, two things happen. Outer corner. There is extra physical copper area at the outer tip of the square bend. This extra metal acts like a larger capacitor plate, pooling excess electric charge. Inner corner. The current wants to take the path of least resistance, which is the shortest path. All the current crowds tightly against the sharp inner corner, increasing the magnetic field and inductance. Equivalent circuit and impact. A square bend acts like a shunt capacitor and a series inductor. It will cause a portion of your microwave signal to bounce right back toward the source. The fix. We almost never use perfect 90-degree corners in RF design. We use a mitered bend. By physically slicing off the outer corner of the square, chamfering it, we remove the excess capacitance. This perfectly balances the inner corner inductance, allowing the wave to glide around the corner with almost zero reflection. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.